Our two speakers are ready, mourn and edcv. They will talk something about the insecurities of VoIP telephony and how to make use of that. So please give them a welcome round of applause.
So, the title is a bit generic. It's not about all VoIP phones. So what we did here is just took some phones and tried to reverse the code they are running, and look what we can do with that. So first, we'll introduce a bit of context about architecture and what are the motivation behind this work. Then I'll show you some, I explain the typical baseband architecture so that you can know what we are trying to analyze behind that. And then we go in the technical details with analysis of a firmware update image. In this case, we have phones that runs VxWorks, so maybe you are not familiar with that, and we will explain some things we can do with that and how to take advantage. So, yeah. Yeah, okay. And what we can do with VxWorks and what are the advantages and disadvantages of it. And a bit of reverse engineering with IDEA for compatibility purpose, obviously. And then we will show how we managed to generate a rogue, to regenerate a valid firmware to make a rogue update to this kind of phone. And then we will discuss next direction we can do after this work. Okay. So the introduction. So embedded systems are everywhere, you might know that. And here we are focusing on customer premises equipment. So it's any telecom equipment which is connected to a telecommunication infrastructure, but which is located at an end user home or at work, but it's outside of the telecom operator. So it's equipment you don't really own. So maybe you own it or it was lent to you, but it's always connected to a telecom operator network. So it's interesting because sometimes these devices are trusted. It's the case of the set-top box, for example, which are generally on a private network of your favorite internet provider. So when it's the case, it means that if you manage to get access to this device, you will probably have access to some network you're not supposed to go. Also, they are telecommunication equipment, which means that it's obvious they have some spying capabilities. Actually, they are even used for it. You know that if an operator needs to look at your traffic, some modem implements a function to sniff all the traffic that goes through your modem. So you can always turn a CPE in a customer premises equipment into a spying device. And also it's always located close to an end user. I mean always, it's generally close to an user. So if you need to target someone, this kind of device are quite useful. So here we are focusing on the firmware update, the firmware management actually, because we want to get access to it. So we want to analyze the code that runs on it. So you know there is always an update system on this type of devices because they need to address security issues, even if it's generally quite late when they do that. Sometimes they need to fix bugs, but generally when they do that, it means the bug is really blocking for them. And generally also when you get the first The first model of CPU, it generally has a lot of unstable features because everything was not released on time. So you always have some updates. You even have to update the BIOS of your motherboard now. Otherwise, it doesn't work. Doesn't really work on the first time. So we want to take advantage of it because if you have a firmware update system, it means that you can either download the firmware when it's manual or you can sniff it when it's automatic. Because your modem generally, when it's updated, you don't have to download the firmware update image. The operator decides for you that your modem needs to be updated, and then the downloading and flashing of your modem will be done automatically. Okay, so these firmware images, they provide a lot of information because they might contain the whole file system if there is of the devices. There is all the code. You have also all the certificates. Everything that is needed to authenticate the firmware and authenticate the device, maybe. Well, it's something that you can really try to analyze to get some information on any embedded system. It's not just for CP. It's just if you want to know how a camera is done, what is the architecture behind it, you can just download the firmware and see what operating system is running on it and on which processor and what kind of ASIC or DSP there is, not for a camera, but for anything. Okay, so it's an alternative method of doing it rather than using JTAG, which is the usual way of analyzing an embedded device. So the advantage of this method is that you don't need a physical access to the device. You don't need any hardware or software which is specific for JTAG, because you need a probe for JTAG and you need software that, you need the JTAG servers that will decode for your processor or DSP exactly, and then you can put a debugger on top of it. So instead of it, we will be using xdump, which is, not as useful as what you can do with the JTAG console, but it's still giving a lot of information. And the downside of this method of analyzing the firmware update is that, contrarily to JTAG, you don't have access to everything. You can't modify values in memory during runtime. You can't dump information. You can, the only thing you can get is what is inside the binary. So now I will show you just an example of baseband architecture. So the baseband is the chip that is connected to the telecommunication infrastructure on one side, and on the other side it's connected to if it's a modem, it will be an Ethernet connection. If it's an SDIO card, it will be SDIO. If it can be SPI, it can be PCIe, it can be anything on the other side. So it's just a chip that that is directly connected to the to the telecom infrastructure, and generally only manage the layer 1 and layer 2 layers of for the network. So here it doesn't really, it does the voip actually, so yeah. Well, let's go. So it's a typical, on n'a pas de pointeur laser. So it's a typical system on chip for a baseband. It's exactly the same architecture you have for an LTE, actually, an LTE chip or a WiMAX chip or a 3G chip, and here it's for a VoIP. So you have the analog front end, which is connected to your RG11 telephone line. And on the other side, since it's VoIP, you generally have Ethernet. But here for VoIP, the Ethernet is used for something else. It's for the replicating. Actually, it's not It's a generic scheme. So you have a flash and a RAM, and inside the system on chip, which is what we will analyze only this part, you have a processor, a simple processor, generally ARM or MIPS. MIPS, it's generally when it's plugged in the power supply because it consumes more than ARM, but ARM is cheaper, ARM is more expensive, so that's why we'll choose MIPS if you don't have a power consumption problem, and if your power consumption, if you have some issues with power consumption because you're running on batteries, you will choose an ARM. And then you generally have a DSP, which is talking to the analog front end, and an ASIC, which is accelerating all the layer 1 processing. So what we are interested in here is having the content of the flash, and we can download it from the internet. So here is the correct scheme for the chip we will be focusing on, which is Broadcom 1101 voip Ethernet CP engine. So you still have the flash, the SDRAM. Here you connect the analog front end. Here you have the Ethernet port, and here you have what I was talking about, like SPI serial or GPIO. And you have the MIPS, the DSP, and the JTAG. So it's where you want to plug in if you have what it takes to do it. Yeah. And here it's software that runs on this, the classical architecture of the software that runs on this chip. So I've divided into, because several actors are implicated in this kind of design. Generally, the operating system, real-time operating system, is provided by an external entity. So here, the example for baseband, generally you will find VxWorks. It was 75% of market share 5 years ago. Now it's more and more Linux instead of VxWorks. You can have RT Linux, Monta Vista Linux, because you have Nucleus, QNX, a lot of real-time operating systems that have a small footprint. This operating system comes with applications and services, which is a vector for vulnerabilities, because generally it's not up to date, and you always have some very outdated applications that runs on it, and sometimes they forgot to deactivate it. Then you have the system on chip manufacturer. So here it's Broadcom, the company who made the chip itself. So they need to provide the board support package and the L2 stack for the baseband. And then you have the final, the original design manufacturer, which is the company to which you will buy your wall device. So here it's Astra, we will see. And so it's just to show that when analyzing this blob of code, you will have at least three very different parts of the code. Okay. And then,
so I will talk now, hello everybody, about how to analyzing the firmware update format. So we will manually use some standard Unix tools, command line tools like xdump, strings, dd, and file. So this tool for beginning will help us. We will be focusing on voip phone using the Broadcom BCM 1101 system on chip that he has been talking about previously. We already know that it's MIPS 32 bits, probably big endian. And so we have been working on the Astra brand. Astra sells on consumer equipment going from simple SIM phones to phones with more functionalities, like they have extension, you can call more people, you can transfer call, and so on. And they are plugged on your most company's network. So the model has a 6753E, which is a new version of the 53E. So when we look at the file, we downloaded all the firmware from Astra website. which is a big zip with many firmware for every model of it. So the first thing we do is file on the command file, which tells you it's just binary data. So looking with xdump, we will start to look for some known patterns like file signatures. People doing reverse mostly look for MZ pattern. Here we are looking for maybe compression algorithms. And at offset 116, I guess, you have here 1F8B, which is the header of gzip stream data. So using DD, we can guess that the first integer is the offset to the gzip stream data. So with DD, we extract it to a new file, and we unzip the data we have extracted. There is nothing else after the gzip data in the file. So using file again, we still have just data. So xdump give us nothing more. So we'll use strings to look for non-string, anything which can help us guess what is in that file. On looking for some pattern, we were able to find that there was this line, which is the boot command line option for VxWorks. So now we are mostly we can guess that it's VxWorks, which we know is loaded at x 0x1000 4000 in memory. It's MIPS big endian, as we already told it, and it's flat memory model with no MMU. This is for performance. This means that all tasks are running in the same memory space. So now we will try to load our image in IDA. And the problem is that we have actually no information at all. No function, no references, no strings. No, you can see that on the top, the analysis bar is still brown because nothing has been analyzed yet. So the point here is to find some information in the file, and we'll try to reconstruct the symbol table. So for this, we will use again our command line tools. First one, we try to look for non-function from VxWorks. VxWorks are one function which is sysinit. It's the main initialization function, which is called most of the time at the startup. It's mapped at 0x8000 and 4000. So using grep, we will find the offset of the string in the binary, and we compute then the real address of the string. Sorry. So the address we just add 0x800 4000, which give us where is located the string in memory. And we then search this address in the binary. The objective is to find one entry of the symbol table, which will contain the pointer to this string. So the first address we get, upon we get the same 8000, 4000, we get one entry of the symbol table. From there, we made a simple script which finds the start address and the ending address of the symbol table. So we goes back in memory until we found 16 null bytes binding area, which is just before the starting address of the symbol table. And to find the end, we do the same process, browsing the memory until we found 16 null bytes, followed by, I guess, 0xFFFF7FFF. And this is the end address of the symbol table.
Well, just to give a little bit of context, VxWorks come with a shell, which is actually a debugger, and the commands you give in the shell are in C, assembly, or ADA. So since you can call any symbol, it means that VxWorks is always shipped with a symbol table and all the address of all the functions so that you can call them in the shell. So we've taken advantage of that, knowing that there is a symbol table which is in VxWorks proprietary format, to try to find it and then to give it back to our disassembly software, which is IDA. So that's why we were looking for the pattern to where it could be in the binary, and so that was the
So we have now we have the starting address and ending address of the symbol table. We will use this later, and now we have to type the memory in IDA so that it will be able to make further analysis later. So we will create each entry of the symbol table. So this is the format. You have a SymTab ID, which we don't care. The second, which is, I guess there may be an error. The first symbol is the name, yes, it's okay, is a pointer to the string in the string table. On the second, the value field is the real address of the symbol. Just swap the comments. And then in type, there is not much. On groups contain the flags. And this flag will tell where relies the symbol, if it's in the BSS, data section, or text section. And this will be important. So the first thing, for each entry of the symbol table, we use makeDayWord and makeWord to create the appropriate types. And then using make function, we can tell to IDEA, okay, at this address, this is a function, and it will make IDEA start the analysis and build the graph and references. And then the last one, make name, it helps you push a new function in the function list on the left one, so that you can search for function more easily later. So after this step, running the script, we get this version of IDEA. So you can see now we have function name, we have cross-references, so we can browse more easily the file. On the top bar, the analysis was done on, I guess, a quarter of the memory. And you have symbol resolution. So now we can use really IDEA. We will look for interesting function. So most of the time, function related to authentication. So we look for pattern like auth, login, user, password, access, all those strings which can lead you to some interesting function. And in this binary, we found the login user add function, which was called from user security and user roots. And so thanks to cross-references, we can go back in the backtrace the function to get its parameter. And so in user security, we found that here on the last three lines, you got two variables pushed in, well, not pushed, put in the parameter register. Obviously, the first one looks like a username, and the second one is some kind of hash. So we had to reverse the hash function to know if we could break the password in some way. So we have found the login default encrypt, which is called later in the call graph. And after a few reversing, we have come to a quite simple algorithm. So this just compute a simple CXC, adding each character of the password with XORing it with its position in the string. And then it multiply it by a magic number. What is, on the last section, it's translated to in a ASCII string. So that means memory, it's just, well, it's translated into ASCII, but there's just a second pass of encoded, which swap some character to some others. And this is the way the hash is computed. What is wrong in this computation? So this is a mathematical function. What is wrong is that it multiplies two integers, which lead sometimes to an integer overflow. And the hash is truncated to 32 bytes. This brings many collisions and can probably be easily brought forced. So we have wrote a simple treat using some single pattern, which is just the password is going from 8 characters to 40 characters. So we set a first character, and then for the last one, we just pad it and try it. It's some simple breadth on here. So on this hash, we were able to find, I guess, 9 collisions. And we have tried on some others, it mostly always finds some collisions. And so here it is now. We were able to log on the phone using telnet.
Yeah, because the telnet was in this kind of phone, and it's not the only one. The telnet from VxWorks was still up. So if the phone is on the same network as the other computer, anybody can log in. And the hash we've just reversed was the default hash of VxWorks. So basically, anybody can take control of the phone. And since you have a shell where you can call the C symbol, it means that you can, well, if you want, you can turn on the microphone and call someone and turn on the microphone so that you can just listen to whatever is saying. Okay, so now we'll look at how we will finish the firmware analysis with the authentication method, because there were some in a previous slide. I don't know if I can go back. Yeah. Here, the part in white, we still haven't decoded it because the first one is just a size, and then we have the JZip binary image. And between this is just some random numbers. Okay, here, and we can first see that there is some 3 ASCII character, which is generally a signature. So there might be something to look for to decode this data. Now that we can reverse anything in IDA, we just try to find the function which is responsible for flashing the new firmware and first authenticating it. And this function is a method of the fwguard class, which is from new firmware. And first we see that it looks for the size. The only invalid size is 0 for the data we still don't know anything about. And a little bit later, it will code fwds codec, which is a void, and the method transform. And it seems to be the function that is responsible for not authenticating, but at least verifying the validity. So since, here it's because we first look a bit at it. So the class fwdes codec, which is used as a function in its attribute, class in its attribute, sorry, which is triple des, which has also a class in its attributes, which is des. And we've tried with Google with a prototype directly, the prototype of the DES and triple des function class, and it led us to this site with an implementation of DES, which is quite well, not very well. It's notebook DES actually. It's not even CBC, but it's triple des at least. And so when looking at the code which is available on this site, because we found it through Google, we find the signature, which is in decimal here, but it's exactly the same. So we seem to have found the software responsible for this. And you have to note also that OpenSSL is and libcrypt are statically linked in the binary image. So it's another example of a company that used their, well, instead of using OpenSSL, which is used everywhere in their code, they just used some weird implementation of DES, which is not even completely correct. Anyway. So now we have found the signature, which is 16 bytes, and after that we know that it's a DES or a triple des, in this case, version of something. So now we want to find the key. So we directly go to transform, and Now it's really easy that we have all the symbols, because otherwise reading the MIPS assembly is not this, I don't know, easy. So we are interested in this function, which is its password, and it takes a const_char star in, as an argument, which is probably the key. Well, from the code we've downloaded before, we know it's the key. And well, just a reminder that since we are in C++ and it's MIPS, MIPS gives the first 4 arguments in register A0, A1, A2, A3. And in C++, the first argument is always the class. So we don't care about this one. We care about this one, which is the key is located here, actually. If we go back in the code, we find the constructor of the FWDES codec, which takes a lot of input. So even without doing the full analysis of it, we notice that V0, the last argument actually, which is probably the key for the triple death, is given in V0, well, it's pushed on the stack and it was in V0. And so we just dump the table and we have a lot of ASCII strings, and ours is here. So the problem of, using a symmetric encryption algorithm for this kind of thing is that you will have the key in clear in the binary image. So now we just with DD we just split the firmware update we had, and we decode with the triple death implementation we found and the key we found later, and we get this this clear text, and the MD5 sum is the gzipped image actually. So it's some kind of validation of the firmware. Okay. So now that we have the keys, it's trivial to generate a rogue update, because we just have to make the same header with the MD5 sum of the file we want to of the image we want to flash on the telephone. Then we just encode it, and with a long line. A long bash line, we can just print the 2 hexadecimal number, well, the short big endian, which is used for the size of the header, and then we just concatenate the gzipped image at the end, and we have a valid firmware. Okay, so just to sum up, the security in this firmware update resides in the check of MD5 sum of an image, which is in a header, which is symmetrically encrypted with triple S, and well, it's useless because we can find the key, and even the image is not encrypted. And normally, if you want to authenticate and without leaking information, they should have use a public key authentication, so that only the certificates would have been, you could only find the certificate on the image, and you know that the certificate doesn't, well, it's just a public key, you don't care about it, it's not useful for reconstructing a valid firmware image. So here it was on a specific telephone, because it's the one we had at this time, but not that it's not the only telephone which is in this case. Okay, and the reversing made trivial with the image and all the symbols. That's funny. Okay.
So for the work, we were thinking what we can do with this. I don't know if you know how voip phone works now. Most of them can get some configuration on boot. It relies on known technologies, DHCP, HTTP, FTP, how it works. When some VoIP provider gets some new phone, most of the time he will scan the MAC address and put it in a database. And the VoIP provider on the other side will tell, okay, I have a new customer, I give him this phone with such a MAC address, and it will have such parameters. So parameter as SIP account, password, registrar server. Eventually, you can also push some a few contacts that you want everybody in the company to have. And if they don't have to put the phone out of the box, you just take the phone to your client, you put it on the network, and it will fetch the configuration by network. What it does mostly, it does a first DHCP request, and it will look for the next, some of them will look for the next server option, which will point to some whether TFTP server, HTTP server, and they will ask by default first default configuration file, which it could be brown.cfg, brown.xml, and then a specific configuration file which is identified by the MAC address of the phone. And for many phones, it's also possible to push the firmware through this configuration file. So this means that whether if you can get on a network with VoIP phone, with some ROC DHCP server, you could push some update to those phones, and by compromising the server, of course.
Okay. And well, just to sum up what I said at the beginning, because since it's a telephone, you know that you can call back someone and well, just call someone and turn on the microphone, which means you have a direct microphone near to someone you want to spy on, for example. You can redirect calls also. You can do a lot of things since you own the phone of someone else. Also, the ROG update can be used to add some functionalities. So still on like a large-scale spying in a company, for example, because if you push an update, all the phone in the company will have the same update. It's kind of critical because well, it's something you've certainly heard several times here in the telecom industry. The security is completely well, nobody is aware about. There is no security awareness actually. So it could be critical, but it doesn't seem to be a priority. And I insist on it. We did it on this phone. It was quite simple actually, but it's the same for a lot of other phones. Even if it's not always VxWorks, which is very, very useful to work with when you want to debug. And this is the end. Thank you.
Are there any questions? Yeah.
Have you come across any VoIP phones that look like they were actually done with proper security?
No.
Thank you.
Thanks for your question.
More questions? Let's thank the speakers and give them a well-deserved round of applause.